Welcome everyone to the Moldex3D Standard Series training, the first of 3 trainings hosted by Moldex3D for new users just looking to get started with Moldex3D or existing users looking for a refresher. Just a couple admin things before we get started. This session is being recorded and the recording will be sent out to all participants after this training. If you do have any questions after this training, feel free to contact us at any time. Speaking of questions, any questions that you may have during this session may be sent through the chat, and my colleagues will help to answer those questions live so that nobody falls behind. This session is meant to be an interactive session, so it's very highly recommended that you ask any questions that you might have. 2 applications will be necessary to follow along in this session interactively. The first of which is CADdoctor. CADdoctor is going to act as a translator from your CAD system to Moldex3D. And then Moldex3D Studios, where we're going to be spending the rest of our time in this training. It's going to act as the model importer, the mesher, simulation software, and the post processor. So a lot of time we're going to be spending in there. And then a third thing that you will need to follow along interactively is the consumer folder. There is a link for the consumer folder in the meeting invite for this session, and you can go ahead and download that consumer folder right now and make sure that it's extracted. It contains the pre-run simulation as well as the CAD model that we're going to be using for this session. If you have not installed Moldex3D, then feel free to follow along visually, and you can review the recording once Moldex3D has been installed at a later time. As far as the agenda goes, this session is going to be split into 3 subsections, the first of which is going to be CADdoctor and importing a model into Moldex3D. So what are the best practices for importing a CAD model, and what do we do with that CAD model? What kind of simulations can we run? Then we're going to get into a meshing breakdown and setting up simulations. So what type of meshing do we use? And how do we select a material and define a process in Moldex3D? And then the third section is going to be what happens after we run the simulation. What type of results do we typically look at? It's going to be a little bit more condensed, and you can check out one of our advanced trainings, which I'll show later on in this session to get a little bit more information about post-processing. That being said, we're going to jump straight into it. And the first thing we're going to do is open up Moldex3D CADdoctor. Now, CADdoctor might not be located on your desktop automatically. When you install Moldex3D Studio, you will get the desktop icon for Moldex3D Studio, but you may not get the desktop for CADdoctor. So you may have to go into your Start menu and obtain this application. CADdoctor is going to act as a translator, like I mentioned previously, from your CAD system over to Moldex3D. When you export a CAD model from your CAD system, sometimes the tolerancing or the definition for service connection or small services, things like that, can actually cause a small amount of issues when we actually go to convert the model to a mesh object in Moldex3D. The quality of the mesh is very important to us, and we want to make sure that the model is reflecting the preferences that we have for a CAD model coming into Moldex. All right, so let's go ahead and open up CADdoctor. We recommend every CAD model, everything that you export from your CAD system with the intent of using in Moldex3D, we recommend that you run those through CADdoctor. And the nice thing is CADdoctor is actually a very, very simple program. As far as the procedure goes, there's only 5 buttons that we're going to be clicking. The first of which is once you have CADdoctor open, up towards the top, there's a little, it looks like a page with a blue arrow. That's our import icon. So import is going to allow us to import either a step file, which is quite universal across pretty much every CAD system out there, or you do have the option to import your native CAD files as well. So you can see things like your cat parts, parametric files, parasolid files, and a bunch of others as well. One thing to note is that we do not have the capability to import a SolidWorks file. So for those of you that use SolidWorks as a CAD system, you will need to export the step file from SolidWorks in order to import to Moldex3D. What I'll ask everybody to do is go to the consumer folder that I just mentioned that you should have downloaded. And we're going to go into the CAD data folder, and that's where you will find the step file for this session. All right, it should be called consumer.stp. You can go ahead and import that. All right, so step one completed. Now we just have 4 more steps to go. The second of which is going to be the check function. Actually, the next 3 buttons that we would click are over here on the left side of your screen underneath the what we call the defect table here. All right, so right underneath this, you'll see 3 buttons that are lit up. The first of which looks like a cube with a magnifying glass. That's our check function. The check function is going to run a 16-step process that will identify any sorts of errors that might have come over from your CAD system. These errors are going to be split into severities, which are a categorization for how crucial it is to actually fix that error. Those 3 categories are critical, serious, and minor. Critical errors, we've always fixed these if it's possible. And luckily, most of the time, these critical errors are going to be fixed through the automatic process. So it's very rare that you actually have to interface with these manually. But if you do have critical errors left over after the automatic healing process, I definitely recommend you to at least take a look at where those errors lie, and you might have to make some alterations to a surface in your CAD system, potentially. The second type of severity is serious, and we recommend to fix these if at all possible. A little bit less serious or little bit less crucial than the critical errors. Serious errors, we do want to get rid of those as much as we can. If there are any serious errors left over after the automatic healing process, I would take a look at them. It doesn't necessarily warrant going back to your CAD system like the critical errors do, but if you're left with any serious errors, I would definitely pay attention to where they lie. And if you have problems in the mesher, then you might actually have to go back to your CAD system and make some adjustments. The last type of severity is a minor error. So minor errors, we pretty much just leave these alone. They're more of just an indication than anything. Sometimes you'll see these are narrow surfaces. Sometimes they're just really small feature lines. Those kinds of things will show up as minor errors in CADdoctor, and you can ignore them. If there's any minor errors left over after the automatic healing process, you can take a look at them, but there's no need to fix them. The third step of CADdoctor is going to be next to the check button, just to the right of it, and it's called Auto Stitch. Auto Stitch, which is currently grayed out for us, is going to allow us to merge 2 surfaces together. And it's directly tied to an error called the loop of free edges. A loop of free edges will occur under 2 circumstances. Either a surface is completely missing, in which case you'll see that the loop of free edge surrounds that missing surface, or 2 surfaces are disconnected from one another. If that's the case, then you'll see a loop of free edges between the 2 surfaces that are disconnected. The auto stitch tool helps us with the second scenario where 2 surfaces are disconnected from one another. It helps us to merge those surfaces back together and almost applies what Moldex3D expects as far as a surface merging tolerance. All right, this sort of problem occurs pretty often with some native CAD files. I wouldn't say pretty often, but um, it happens on occasion with native CAD files, and even sometimes step files as well. Sometimes all of the surfaces will just be what we call dissociated from one another. The surfaces will be all disconnected, and then the auto stitch tool will help you to connect all of those back together. All right, the fourth button, the fourth step of CADdoctor is auto heal. And auto heal is going to attempt to fix everything else besides the loop of free edges. So when we use auto stitch, that's going to help us to fix the loops of free edges. Then the next button to the right of that auto heal attempts to fix everything else. Now it's actually going to run the healing kernel, and then it's actually going to automatically press the check button for us again. So it's going to update this table for us based on what errors are left over after the automatic healing process is completed. All right, so we can see in this case, and this is what you should expect for most cases, is that we're left with just a couple of minor errors after this automatic healing process. Even if you have thousands of errors, CADdoctor is really consistent at healing your model for the most part. So you'll be left over with maybe some serious errors, but mostly just minor errors after this automatic healing process is completed, which really helps us to make sure or to confirm that the model is good quality going into Moldex3D so that we can minimize the amount of effort that we need to give to the mesher. All right, so just as a recap, we clicked import, check, auto stitch, auto heal, and then the fifth and last step here is simply export. So right next to where we clicked import earlier is going to be a page with a red arrow that allows us to export the model. All right, so you can save this model to wherever you want. I'm going to go back into my consumer folder and we'll just throw it into that CAD data folder once again. The save type or the extension that we're going to be using for the models coming out of CADdoctor is MDXSF. MDXSF is a Moldex3D specific file type, and you'll only be able to import this into Moldex3D functions. That being said, you can export an MDX, and once you import this MDXSF, you do have the option to export that as a step file through Moldex3D Studio. So if you wanted to use CADdoctor as a means to fix your model for other applications, you actually can do that. All right, so we're going to go ahead and just save this MDXSF file. It might beep a couple times. And once you've exported your model, that's really all we need from CADdoctor. Now, if I have a runner system that I've exported from my CAD, if I've exported my cooling system from my CAD, all of these objects, I always recommend to run through CADdoctor to make sure that the servicing is as clean as possible so that our meshing life is a lot easier. All right, but once we're done with CADdoctor, we can go ahead and close out of the application. And it's going to ask us to save the model. This message actually looks like we're going to save the step file at first glance. It's actually going to save the application file for CADdoctor in an extension DRFX MDX, and that's essentially just going to be a save point for CADdoctor itself. So if you wanted to save your model and then maybe instead of going through the whole process again, you want to open it up and just continue from where you left off, that's where the DRFX MDX or the application file for CADdoctor comes in handy. But most of the time, once I've exported my once I've exported my MDXSF file from CADdoctor, I don't really need the application file anymore. All right, so moving on, we're going to jump right into Studio. So we were just in CADdoctor, so now we're going to jump into Moldex3D Studio, which is where we're going to spend the remainder of our time here in this training. While this opens up, I can't emphasize enough how important CADdoctor is to this process. Once we get into the meshing, you'll definitely start to notice how much value you're getting out of CADdoctor because it's going to help you to streamline your process, and it's going to make your life a lot easier when you go to convert your solid model to a mesh model. When you open up Studio, you're going to be faced with two options. You can either open up an existing project or you can create a new project. In this case, we don't have an existing project, so we're going to go ahead and create a new one. All right, the default name is going to be MDX project with the date. That's how it's always going to be. I recommend to change this to make it more meaningful. I'll call it standard training with the date, but you can call it whatever you want it to be. And then the location by default is actually going to be the MDX working folder. The Moldex3D working folder is something that was created when you installed Moldex3D on your computer. And most of the time, we recommend to put this working folder on your local drive. And this is very important because if you put the working folder, if you put your simulations on a network drive or a shared drive or even an external hard drive, the simulation time is going to be a lot longer than if you put the simulation on your local drive. And the reason for that is because every time there's a data transfer, it has to go across the network, which is a lot slower than what your local computer can do. All right. So we always recommend to put your projects on the local computer for simulation. And then once the simulation is completed, you can feel free to move those projects wherever you want to. All right. You can also create your own subnetwork of folders. You actually saw a subfolder that I just deleted there. You can create your own organizational tactics inside of your working folder. And you don't even have to put these in the working folder. You can create your own structure. You can create a job structure layout, nomenclature, whatever you want to call it. You can do whatever you want. Just make sure that your simulations are on the local drive. We can press OK, and that will create our project file. The project file is where all of the simulation inputs as well as the simulation outputs are going to be saved. All right, so the simulation project is going to house a series of runs. We can see the first run is created for us automatically here. So if we wanted to create more iterations, if we wanted to create more runs, all of those would be in the same simulation project. All right, so that's very important because in every different model that you do, I recommend to create a new project for so that you can keep the organization as reasonable as possible, or as yeah, I guess reasonable is probably the best word for it. So just a small note, you don't want to have multiple jobs or multiple models running around in the same project. I always recommend to create new projects for new models. That being said, the procedure for Moldex3D is extremely straightforward. All we're going to do is follow from left to right across what we call the ribbon, which is at the top of our screen. This ribbon is going to just hold all of the buttons and all of the knobs and tools that we're going to need to guide us through Moldex3D Studio. As such, we're going to start all the way at the left side, and we're just going to go to the right side. And Moldex3D, for the most part, is just going to route us around the interface automatically. If you're ever stuck at any moment, just go back to the last button you clicked on, move to the right of that, and that will kind of get you to the next step. All right, very, very straightforward. Starting at the very left is where we can create new runs. The first option, if you click on the drop down here, is new run. This will create a brand new blank data set. So it'll allow you to start from scratch. Like I mentioned before, Moldex3D does create the first run for us automatically. So you don't really have to go through and create a new run right now. But if you wanted to create a brand new run from scratch later on, you could use the new run to do so. Copy run is probably the most common way to create new runs in the Moldex3D Studio interface. And the reason for that is most of the time we're going to run a simulation, then we're going to copy that run, make a small change, and then run the simulation again to see the impact of that change. All right, so copy run is going to end up being the best iteration tool that we have available to us. Copy run allows us to just copy all of the information from a particular run. Then we can make whatever change is necessary, and then we can rerun the simulation to see the impact of that change, like I mentioned. The third option here, import run allows us to, well, import a run from a different project. So, for example, a very common simulation tactic that I've seen is maybe a part designer will run a gate location study, and then that study is passed to a mold designer to start designing the cooling system. Now, you don't want to just send those projects back and forth, so maybe you just send a single run from the part designer to the mold designer, and the mold designer can import that run and start making the iterations from there. The last option in here, DOE, stands for Design of Experiment. This allows us to create a matrix of runs, almost as though we're pressing the copy run button a bunch of times and um, making iterative changes. All right. The DOE function is locked under the expert module, and the expert module is an add-on to your base package. All right, like I mentioned, we don't really have to do anything here because Moldex3D creates our first run for us. So we'll just move to the right of that to the molding type. The default molding type is always going to be injection molding, which is what we're going to be using for this training. And you can click on the drop down to see a bunch of other advanced processing methods as well. Things like compression molding, gas assisted injection molding, and a bunch of others as well. Like I mentioned, for this session, we are just going to be using injection molding, but feel free to explore around the interface if as much as you want to. Moving on to the right of that is where we're going to import the model that we just got out from CADdoctor. By default, it's going to say build model here, so you can go ahead and click on the drop down and go to import geometry. This is the option that I always recommend to use when importing the file from CADdoctor. The other option here, import geometry auto heal. This is a beta version of CADdoctor essentially. So this is kind of importing the geometry while running it through CADdoctor. Unfortunately, at the current moment, the auto heal import takes longer than what we would recommend to most users. So for that reason, we don't recommend to use it as of right now. Import geometry is going to be a lot more straightforward, and we've already used CADdoctor. The last option here, import mesh, is going to allow you to import a solid mesh file, which is called an MFE file. That allows you to import an already generated mesh, so you don't have to go through all the meshing stages. You can just import the mesh model straight away. All right, we're going to go ahead and use import geometry, and we're going to find that MDXSF file. So I saved mine in the consumer folder. And you can go wherever you save the file from CADdoctor, and we're going to import that MDXSF file. And it imports just like any other CAD file. All right, once you've imported that CAD file, there's a couple of mouse controls that I'd like to go over. First of all, rotation is going to be right-click drag. We are working on customizable mouse controls for the next version, but right now, right-click drag is going to be your rotate in Moldex3D Studio. Zoom in and zoom out is simply just going to be your middle mouse scroll. If you hold the shift button on your keyboard and right click and drag, that's going to allow you to pan your model or translate your model. And then control right click drag will allow you to zoom in and zoom out a little bit more controlled than what you would have with your middle mouse scroll. So it just gives you a little bit more fine zooming control. Now, something that we're going to be using quite often is selecting an object. So to select an object, all you have to do is left click on it. All right, that turns all of the feature lines on your part from blue to yellow. and it's just kind of an obvious indication that you have selected your model. But there are a couple of other options that you have for selecting as well in the form of what we call box selects. So box selects are going to be enabled through a left click drag. And if you left click drag from left to right across your screen, this box will select anything that is completely encapsulated within the boundaries of the box. All right, so if I don't get my whole model, it's not selected. And you can see that you can even go from the bottom of your screen to the top of your screen as well. The other type of box select is going from right to left across your screen. This box will select anything it comes into contact with, whether it's completely surrounded by the box or not. If I only partially get my box, or if I only partially get my part with the box going from right to left, it will be selected, whereas going from left to right, it would not be. All right, so those box selects will come in handy in various stages of your design process. Now you can see that the interface has transitioned from the Home tab where we started over to the Model tab. It's done that for you automatically, and that's something that's awesome about Moldex. It'll kind of route you around the interface automatically. I'll stop for a moment just to mention to everybody that just joined, if you do have any questions at any time, feel free to send those into the chat, and my colleagues will help to answer those live. Now that we've transitioned over to the Model tab, we can start all the way to the left, and we're going to continue on from left to right across the interface here. Starting with import geometry. In this case, we don't have any other geometry to import. We're going to be using Moldex3D's wizards to generate a majority of our model. But you can go ahead and import more geometry. For example, if I had my runner system as a CAD object, my cooling system as a CAD object, any inserts, all of those could be imported using the import geometry function, just like we imported the part here. But because we don't have anything to import, we can move on to the right of that where it says check geometry. Check geometry will check for two main things, the first of which is free edges, which is synonymous with the loops of free edges that we saw in CADdoctor. If any free edges are located on your model, you'll see instead of a blue feature line, you'll see a red feature line instead. And free edges are the exact same indication, whether we have a missing surface or just two surfaces that are disconnected from one another. If you do see that two surfaces are disconnected, then I definitely recommend you to go back into CADdoctor and merge those surfaces together using the auto stitch tool. The second type of error that's output here is the tiny edges. Tiny edges, just as the name might suggest, are very small feature lines on your part geometry. In this case, we have one tiny edge, and we can use if you highlight tiny edge and then use this little magnifying glass here, that will zoom you to where that error actually is. And then if you rotate around a little bit, you'll actually be able to see that particular tiny edge. Now, the reason tiny edges are indicated is because of how we do our meshing. Ultimately, we're going to be converting every surface on our model to a series of triangles. And every feature line is going to represent at least one edge of a triangle. So for example, if my triangle size is relatively large out in the middle of my surface here, we can see that this feature line is going to dictate that the size of the triangle is going to need to be really small, which means that eventually I have to go from the large size triangle to a smaller size triangle. And that mesh size disparity can actually cause a propagation of error in the simulation. When I say error, it's more of just like an inaccuracy in the simulation due to mesh quality specifically. All right, we want to avoid that as much as possible, so reducing this tiny edge count as much as you can is very highly recommended. However, you don't need to reduce it to 0. Having a couple tiny edges, I say a couple, really anything less than 10 is fine. Even for more complicated models, somewhere maybe even like below 100 might be fine. But once you start getting into the larger amount of tiny edges, then you might actually want to consider simplifying your model a little bit so that you can so that your meshing life is as smooth as possible, and so you don't have that potential for a propagation of mesh disparity. Now we do have a couple of other options as far as fixing the model in Moldex3D. We have a sew function, which is pretty synonymous with the auto stitch tool in Moldex3D or in CADdoctor. However, I would recommend to go to CADdoctor and use the auto stitch tool over this sew function, as the stitch tool is a little bit more powerful and you have a little bit more control over it. We also have the ability to delete faces and fill faces back in, which is great. If you do have a missing surface, fill face can allow you to fill that back in. But keep in mind that if the surface is contoured, something like this guy right here, the fill face might not work as well as you need it to. So in that case, I would also use CADdoctor. All right, so we can go ahead and exit out of the fixed geometry function. You can either press exit here, you can close out of the fixed geometry tab, either works. And we're going to move on to the right of this. To the right of the check geometry function is attribute. Attribute is a fancy term that we use for telling Moldex3D what each object is supposed to do in the simulation. All right, so attribute means that we're going to tell Moldex3D, for example, that this object that we've imported is our part. Whenever you import an object into Moldex3D, its default attribution is going to be none, meaning that it means nothing as far as the simulation until you tell Moldex3D what it's supposed to mean. All right, very, very important. So Moldex3D is going to automatically recognize a runner as a runner. It's not going to recognize your cooling system. It's not even going to recognize your part. You need to tell Moldex3D what every object means when you import it. Okay, so that's where the attribute function comes in handy. So we're going to go ahead and click on the dropdown. You can see all the different attributions that we have available in Moldex3D. We're going to go to the second option here, part. You'll actually see that the color of the object changes from a gray color to this more like beige color. All right, so every attribution actually has a different color in Moldex3D. You'll see like part inserts are red, cold runners are blue, hot runners are orange, and you can kind of go down through those and see all the different colors we have available. So you'll be able to discern every object from one another pretty easily. All right, once you've selected your attribution, you can go ahead and press the green check mark. This green check mark is actually quite common throughout the Moldex3D Studio interface. So if I ever say press the green check mark, this is what I'm referring to. All right, you can actually see that a bunch of buttons have lit up now that we have a part assigned. So we're going to move on to the right of attribute and go to model thickness. Model thickness is going to create a very generic mesh on our part. And from that mesh, we're going to discern the thickness plot. All right, the thickness plot is actually going to be, you're going to see some anomalies just because of how that mesh is generated. But for the most part, you'll see that the surfaces on your part will have a pretty clear-cut color to them, or a pretty clear-cut average thickness. Now, one thing to note with the model thickness function, the scale is actually going to be skewed a little bit. Sometimes there are some extreme values that are calculated based on the default mesh is played, which actually puts the maximum a little bit higher than it needs to be. All right, so we're going to go ahead and take that maximum thickness down. And to do that, we're just going to hover over the red portion of our scale. We're going to click and drag, left click and drag that downwards. And you'll see that the color distribution on my part gradually changes. We're going to continue to decrease this until a major surface on my geometry turns red and starts to disappear. All right, so you can see this surface here is much thicker than the rest of my geometry. And I can actually read off the maximum on my scale at this point, and it will give me the actual thickness of that region or of that wall. All right, so in this case, this wall is about 3 millimeters thick, and I can continue downwards until another major region on my part starts to disappear. All right, so this guy might be somewhere around like 2.5. And then I can continue downwards to maybe identify some other thickness regions. So maybe like this surface here looks to be a little bit thinner, maybe somewhere around 2 millimeters. So this model thickness plot is really used as a means to get you familiar with the thickness distribution across your part, specifically for part designers when you're actually trying to model where the gate should go. We recommend not to put the gate in a thin region on your part geometry, as putting a gate in a thin region is going to increase the amount of pressure required to fill the part geometry. All right, so these thickness distribution really just gives you a way to get comfortable with your model if maybe you're getting the CAD design from another designer or something like that. This just allows you to get a little bit more familiar. Now you can feel free to keep this thickness distribution overlaid if you want to. I typically don't, just because sometimes it does get in the way. Sometimes the colors are not all that clear cut and are a little bit distracting. So what I like to do is actually go back to the first tab in what we call the modeling toolbar here. All right, so the first button in the modeling toolbar, right underneath the import geometry, kind of looks like three dots with I don't know, three rectangles next to it. This is what we call the project tree, and the project tree is where we're located. That's actually where we started. And if I click on model in the project tree, that will get rid of the color distribution and return us back to the blank model. All right, so that does it for the import and analysis section. We're going to now move on to designing a feed system. All right, so you can actually import your feed system if you want to. If you have the CAD geometry of your runner, you can always feel free to import that directly. However, I always recommend that um, if maybe if you're just seeing this for the first time, you can actually use Moldex3D's gate wizard to place a gate on your part geometry, and you can just run a very generic simulation to see how the plastic is going to flow through the part. All right, you can either add a pin gate by using the function here. You can click on the drop down and select a bunch of other types of gates as well, things like edge gates, perimeter gates, things like tunnel gates, cashew gates, a bunch of others here as well. In this case, I will just be using a simple pin gate, but feel free to explore a little bit if you want. And the way the gate wizard works is we're just going to hover over a surface on our geometry, and the closest surface to our cursor is going to be our gating surface. Moldex3D will automatically create the gate normal to that surface. And I say normal because actually if I were to put it on the curved surface, you'll see that it'll actually follow the curvature of this surface, which is pretty cool. So it'll always be perpendicular to the location that you place it. All right, so I'm just going to place it in the middle of this nice flat surface here, or generally flat surface. It's not perfectly flat, but you get what I mean. And from here, we actually get three different parameters. The first of which, or the first two, are going to be different diameters. So you can see that above the diameters, there are two dots. There's a red dot and a green dot. Those actually correspond to the two dots that you see on the gate. Now, the cool thing about our gating in Moldex3D is that we use what's called line definition. Line definition means that we're actually just creating a one-dimensional line, and then we can define the three-dimensional properties based on the inlet diameter, the outlet diameter, and the gate length. All right, and I have the option to change all three of these. The defaults that I get are actually based on the size of my part geometry. So when you import your part into Moldex3D, we automatically recognize what the volume of that part is, and then from there we can recommend a gate size. So it will always be an integer, so you'll never get like 3.694, whatever, it won't be anything wacky. It'll always be rounded to the nearest integer. And in this case, it is a 4-12-12 gate. Now, something interesting to note about pin gates specifically is that they will always have the same ratio. That meaning uh, the the inlet diameter is always going to be 3 times the outlet diameter, and the gate length is also always going to be 3 times the inlet diameter. So it's a 1-3-3 ratio, and it's just scaled based on the size of your part. Now, like I mentioned, you always have the option to change this. So if I wanted to increase the inlet diameter, or I guess decrease it, you can change that. And if you change the number and press the Enter key on your keyboard, then that will actually update the model so that you can see what that change looks like visually. And you can kind of mess around with this however you want to. I'm just going to return back to the default parameters, but feel free to make whatever size gauge you want. Once I'm satisfied with the size of my gate, I can go ahead and press the green check mark. And then it'll actually come back into that function, and it'll give me the opportunity to copy this gate as many times as I want to. All right, so you can go ahead and place more gates if you want. In this case, we're just going to be using one gate, but if you want to experiment with more gates, feel free to do so. If you don't want any more gates, you can go ahead and press the green check mark, and that will just complete that function with just the one gate on your part. Now in this training, we're going to keep things nice and simple. I'm not going to go any further than the gate. You can definitely feel free to start designing a runner system. The runner system would allow you to extend past the gate all the way up to the machine nozzle, and actually a couple of improvements in our solver or in our modeling capabilities are actually going to allow us to extend past the nozzle in the future and go actually into the barrel, which is going to be pretty cool. So you can actually make your modeling as comprehensive as you want to, and in most cases, runners are actually quite simplistic, and they're able to be modeled with this line definition pretty easily. So as you start to get more and more familiar with Moldex3D, using this sort of line definition method is actually going to be the recommended method, simply because the mesh is going to be higher quality. And I'll mention that when we get into the meshing a little bit later. The mesh is going to be higher quality, and if you're wanting to mess around with the runner, remember, all you have to do is attribute the gate. So kind of like what we did with the attribution of the part, you can actually just double click on the gate. That'll go to the attribute wizard, or you can use the attribute button. The double click is just kind of a shortcut. And you can make the change, remesh it, run the simulation, without having to go back to your CAD system. So you can do all these sorts of iterative changes inside of Moldex3D, which is really, really convenient and allows you to start churning out analyses and start experimenting with your model without too much of a time consequence. All right, so like I said, I'm not going to make things too complicated. I'm just going to keep my gate. I'm not going to design a runner system right now. But we do need some place for the melt to actually enter our part. Now we've created a gate, which is inherently where the material is going to enter our part, but we haven't actually told Moldex3D where the flow is going to start from. All right, and that's what the melt entrance is meant to specify. So to the right of the runner button is melt entrance, and that will place a red arrow on the top of our gate in this case to indicate that that is where our plastic flow is going to start. Obviously, this would be at the top of your runner system if you did design an entire runner system. There's a couple of other options here as well. You have specify point. So if you wanted to manually specify the melt entrance, you could do so. For a geometry runner, specify face will allow you to click on a surface instead of clicking on the top of this line like we've done here. And then symmetry actually allows us to consider a multi-cavity model without having to actually model all of the geometry. I don't have enough time to get into this too far, but if you do have any questions about symmetry, feel free to shoot those into the chat. Now, if I just want to run a flow analysis, if I just want to see the impact of this gate location on how the plastic is going to flow through my geometry, I don't actually need to go any further as far as the modeling is concerned. I can just have a gate and a part and run a filling analysis or even a filling and packing analysis to see how the material is going to propagate through my geometry. However, if I want to go further, if I actually want to see what the final part is going to look like, if I want to run a warpage analysis, as we call it, if I want to study the cycle all the way through until the part cools down after the cycle is completed, then I need some sort of cooling system. The reason for that is because if we don't assign a cooling system, Moldex3D has to assume that all of the heat in our melt transfers to the environment ideally. So we are going to be assigning what we call a mold temperature. So it's going to be assuming that the surface temperature or the temperature on the surface of our geometry is at a constant temperature, and that's not realistic. The reason for that is because heat is always going to propagate through your mold, and there's always going to be a distribution of temperature through your mold as the heat is transferred from your part geometry out to your cooling system. So even if you don't have a cooling system designed yet, you still want to kind of artificially create a cooling system, what we call a dummy cooling system in your analysis to represent a more realistic molding condition than just assuming an idealistic cooling. All right, so very, very important note, if you do want to run a warpage analysis, we always, always recommend you to create a cooling system. All right, and the cooling system is actually going to start out with the mold base. All right, so the mold base is actually just going to be a very simple box that's going to go around our entire model system. In this case, we just have the part and the runner, but your model system might get more complex as you get more familiar with Moldex. So this box will encapsulate all of those all those mold objects. Now the default parting direction is always going to be the Z direction unless you tell Moldex3D otherwise. And in this case, we want our parting direction. If you look at the axes down at the bottom right corner of your screen, we actually want the parting direction to be in the X axis. So we'll go ahead and make that change. All right, then we can actually start changing the length and width dimensions of our mold if we so desire. For most analyses, if you're just creating a dummy cooling system, the default mold size is actually going to be quite reasonable, but you can feel free to change these if you so desire. You can also start messing with the height. So the W dimension is our width dimension, L is our length dimension. And if you click on the blue arrow at the top, you actually have access to the height dimension as well. Now this red surface in the middle, it actually might look like a parting line or the parting plane between the core and cavity sides of our mold, but actually what it represents is just a projection plane for our cross-sectional area of our part so that we can accurately predict the clamp tonnage in our simulation. All right. So the location of this plane with respect to my part actually doesn't matter. The reason for that is in Moldex3D simulation, we never actually separate the core and cavity sides of our mold. All right. So just keep that in mind. This red plane is more just meant for projection than anything. You don't need to worry about where it is with respect to your part geometry. All right, once we're satisfied with the size of our mold and the orientation of our mold, we can go ahead and press the green check mark, and that will complete the function. Now we have a mold base. You can see that a couple of other icons have opened up for us. The next one to the right of our mold base, you can note that we've never abandoned the left to right philosophy. I'm just going from left to right across the interface here. So the next button to the right of mold base is cooling channel, and that will actually just create a very generic cooling channel layout, which will allow me to at least get some sort of realistic heat transfer condition in my mold, even if I haven't gotten my cooling channel system designed yet. All right, the cooling channels are controlled by 5 main parameters, the first of which is the channel direction, which are just going to be the perpendicular or the orthogonal directions to the parting direction. And I note that we do not allow you to design cooling channels through the platens. The second parameter here is going to be the diameter. You can use these little arrows here to control each of these parameters individually to see what they do. D is the diameter of the cooling channels, which I'm going to keep default here. You can go ahead and change these however you want to, though. N is the number of cooling channels on the top and bottom. So we have 8 on the top, 8 on the bottom. If I decrease this number, and it decreases the number of cooling channels on the top and bottom. I'm going to go back. I'm going to go down to 4 here. C is what we call the pitch. The pitch is the distance between the cooling channel centers. So this just allows us to maybe space out the cooling channels a little bit more. Maybe I can cover my entire parting area. And then H is the distance from the cooling channels to the top or bottom most surface of the geometry. And this is out of these 4 channel parameters here, the height dimension is the most important if you're designing a dummy cooling system like this one. All right, so we actually don't want these cooling channels to be too close to our geometry, because if the cooling channels, like this guy right here, for example, if our cooling channel is too close to our geometry, then this surface, this region of our surface is going to be relatively cool. This region of our surface between the cooling channels is going to be relatively hot. And that variance in surface temperature, as we'll see in the post-processing, can actually result in artificial warpage. All right, and we want to avoid that as much as possible, because the whole purpose of this is to get a realistic heat transfer distribution, not to induce something that's not going to be realistic. Right. So we want to get these cooling channels a little bit further away from the surface of the part. I usually recommend to do 10 diameters. So in this case, I would use a parameter of 80. That's usually far enough away from the part surface to where we don't directly manipulate the surface temperature of the part, but we do still get a pretty accurate depiction of the heat distribution through our mold. All right, you can feel free to copy my parameters here or use your own, but once you're satisfied with your cooling channels, you can go ahead and press the green check mark to complete that function. And once you do, Moldex3D is automatically going to place inlets and outlets on your cooling channels. The blue, or the darker blue side is going to be your inlets, and the cyan side is going to be your outlets. Because of this automatic assignment of the inlets and outlets, we don't actually have to press the inlet and outlet button. We actually skip over that and go straight to check cooling system. Check cooling system will actually run a bunch of different checks. The first of which is just to make sure that all of your inlets and outlets are assigned. The second is to make sure that there's no intersection between your cooling system and any of the other objects of your mold. And also we want to make sure that all of your cooling channel inlets and outlets lie on the mold boundary. This is actually something that gets forgotten quite a bit in Moldex3D or in molding simulation in general, is that your cooling channels do need to be on the boundary of your mold base in order for the flow condition to be accurate. Okay, so you want to make sure that if you're designing your cooling system in your CAD, you want to make sure to put the entrances and exits of all these cooling channels on the same plane so that Moldex3D can recognize those, and you can get all of those surfaces on the same plane when they come into Moldex. All right, so just as a recap here, we have a part and the gate. The part in the gate alone would allow you to run a filling and packing analysis. You really don't need any sort of cooling system to run a simple filling and packing analysis. But if you want to go further past the filling and packing, if you want to study the cooling cycle, or if you want to study ultimately the warpage of the part coming out of the mold that you need to design some sort of cooling system. In this case, we just have our cooling channels and a mold base. As far as the cooling system is concerned, you can also extend it to include things like mold inserts. So if you put like a beryllium copper insert in your mold, or maybe if your core and cavity sides of your mold are different materials, then you can actually bring those in and assign them differently. All right, like I said, in this case, we're going to keep it a little bit more simplistic. But like I said, you can get pretty complicated with Moldex3D. You can really start to introduce a lot of complexities into your simulation to make the simulation as realistic as you possibly can. But at this point, we're actually done with the modeling and we're going to be moving on to the meshing stage. Before that, we're going to take about a 5-minute break. We'll come back. I'm going to have a small announcement before we start again. But we'll go ahead and take a 5-minute break, come back and start talking about meshing and how to set up a simulation in Moldex3D. If you do have any questions for me or for any of my team, feel free to shoot that into the chat function of Teams, and we'll be happy to answer those questions throughout the break. All right, before we get started into the next section, I do want to just make a quick announcement. We do have 3 different online trainings available. So this is just the standard training that we recommend all users to join. But there is actually a couple of other free trainings that we provide as well. You can sign up for these on our website at moldex3d.com. And the first of which is called Advanced Training 1. Advanced Training 1 goes over mold component import and meshing. So how can we actually import things like mold inserts? How can we import part inserts, the cooling system, the runner? How do we build a more comprehensive mold in Moldex3D? Then we go on to shear heating and balancing a runner system. So how can we accurately define a runner system, and how can we use Moldex3D to identify shear heating in our mold? And the last one here is optimizing cycle time in Moldex3D by identifying things like the filling time, gate freeze, and how the cooling is actually impacting our part. Then the second one, we actually have a different training session here, Advanced Training 2, which goes over kind of a more comprehensive post-processing, going over kind of just all the results that we need to know in the filling stage, qualifying the cooling system, and then understanding warpage a little bit better in a little bit more comprehensive way. All right, so feel free to sign up for those on our website, moldex3d.com. You can just search for those, and it is free, just like this one. So definitely come out and learn about a little bit more about Moldex3D. But that being said, we're going to go ahead and continue on with the regular scheduled programming here, and we're going to jump into meshing. So how do we, in Moldex3D, how do we create a mesh? How do we convert the model that we've created here into a mesh geometry? All right, so we're going to go ahead and start out by going over to the Mesh tab. This is actually the only point in the Moldex 3D interface where you need to click on one of these tabs manually. Actually, at every other point, every other instance in the interface, you'll actually be routed around these tabs automatically. You do need to go ahead and click on the Mesh tab here, and we'll just continue on from left to right, just as we've always done. So the first thing here is defining the meshing type. The meshing type, we actually have 2 different types of meshing that we can utilize. The first of which is solid, which is what we define as our boundary layer meshing, or BLM type meshing, which I'll explain in just a little while. And then the second type of meshing, which is a little bit more phased out at this point, is E-design. It's more commonly referred to as a voxel mesh. This type of mesh is a little bit easier to generate, I'll say, from a pre-processing standpoint, but unfortunately, the simulation time is quite a bit longer than a boundary layer mesh, and the results are not as high resolution as with a boundary layer mesh. So for that reason, because boundary layer meshing is actually quite simple and quite easy to generate, we do recommend to use boundary layer meshing for every application. All right, next we'll go into generate. We're not actually going to generate any mesh quite yet. You can go ahead and click no in the little pop-up that might come up there. But this generate function just allows you to see the sequence that Moldex3D is going to use for meshing. All right, so we're actually going to be starting off with what's called a surface mesh. So when we were in the check geometry function, I mentioned that we're going to be converting every surface on our geometry to a series of triangles. That's what the surface mesh is. All right, so we're going to be generating the surface mesh for all of our CAD geometries. In this case, it's just the part. Then we're going to use that surface mesh to generate the solid mesh of the part in what we call boundary layer meshing style. Then we're going to generate the solid mesh of our runner, which in this case is a line defined object. Remember, it was just a line that we've defined as a 3-dimensional object. Same thing goes for the cooling channels, actually. I didn't mention this before, but the cooling channels are also a line-defined object, and then we can mesh the mold base. Something very unique to Moldex3D is that we always use 3D solid mesh. We use true 3D mesh in our solver so that we can get the most comprehensive analysis possible. increases the resolution of our results and really gives us as much information as we need to make all of the assertions that we need to looking at the simulation results. All right, like I said, we're not going to generate anything, so we're just going to go ahead and press the green check mark to get out of that generate function. We're actually going to set up the parameters of our mesh before we generate anything to make sure that we're getting as high quality mesh as possible, to make sure that we're following the Moldex3D recommended best practices. All right, like I mentioned, there's really two main meshes that are going to be generated. There's the surface mesh, and then there's a solid mesh. So we're going to go ahead and set up the surface mesh parameters first through what we call the seeding button. All right, when I click seeding, it's going to ask me to select my polysurface objects. A polysurface object is simply just a multiple surface object. So that would be really just any CAD object in your model. So you can go ahead and select your part and press the green check mark. All right, and it's going to come up with one single parameter called the mesh size. Now to see what this mesh size does, we're going to go ahead and click apply. All right, you can start to rotate your part around so you can see a little bit better. You'll see that this mesh size actually puts a bunch of nodes on my part geometry. These nodes ideally are about 3.197 millimeters apart from one another. Now, that's never going to be exactly true, and the reason for that is every feature line of my geometry has to be divided into an equidistant number of segments. All right, so you're never actually going to be at 3.197. You're just going to be as close as possible to that number for each feature line in your geometry. All right, the spacing of these nodes dictates one side of the triangular element. So you could think of like one element being this node, and this node, right? So as I propagate that to the middle of my surface, you can kind of see how these nodes really dictate the size of my surface mesh elements. And the size of my surface mesh elements are really going to control two main simulation philosophies or two main simulation trade-offs that we really need to take into account. All right, the first of which is computation time. If I decrease this number, let's say I go down to 1, for example, I'm going to increase my node count, which means my surface mesh size is going to get smaller. This is great from a resolution standpoint. We're actually going to get a fantastic resolution in our results, which is really nice to look at. But unfortunately, this doesn't come at a zero cost. We do increase our simulation time when we decrease our mesh size. On the other hand, if I increase my mesh size, let's say I go to 7, we'll go the other way with it. If my mesh size is larger, then my surface mesh element size is larger, which means that the overall number of elements is going to be lower, and a lower number of surface mesh elements leads to a smaller computation time or a shorter computation time, which is fantastic, but it also kind of sacrifices the resolution that we got from the smaller mesh. All right, so we have to find some middle point that gives us a reasonable computation time while also giving us the resolution that we need to really get valuable results out of the simulation. All right, and to arrive at this trade-off or this optimal point, we're going to use what's called the Goldilocks method. All right, the Goldilocks method dictates that we need to be looking down on the top of the part from the parting direction. All right, so you're going to rotate your part around so that you're looking down the top of it. And then you're going to rotate the part around so that the longest dimension is horizontal on your screen. All right, you don't want your part facing like this. You want your part facing so that the longest dimension of your part is horizontal on your screen. All right, and then finally, you're going to zoom in so that the part fills up the entire screen, either from top to bottom or from left to right, whichever hits first. All right, the reason we do this, the reason we have such a specific rotation command set is because we want to normalize the size of the part geometry to our computer monitor. So this actually takes out the size of the part from the equation. This could be 2 millimeters long. It could be 2 meters long. I wouldn't know the difference because I've normalized the size of it to my computer monitor. This allows us to set the node size spacing consistently for every part geometry that we bring into Moldex3D. All right, now as far as the Goldilocks method is concerned, what we're going to do is we're going to decrease our mesh size until there's about, and you'll have to hang with me on this, until there's about 2 to 3 nodes width of space between the black nodes. All right, a node's width of space is actually just the thickness of one of these black nodes. All right, so I want to be able to fit about 2 to 3 of these black nodes in the space between the black nodes. Hopefully that makes sense. And it's going to be more of a visual approach, which is why we call it the Goldilocks method and nothing more scientific, because it's not really scientific. So if I decrease my mesh size, we can see that the node spacing, maybe this is somewhere like 4 to 5 nodes width of space. I can continue decreasing it. But if I decrease it too much, let's say I go down to 1, we can see that there's no spacing at all between the individual black nodes. That indicates that it's too small of a mesh size. All right, so then we can start increasing. Maybe this is like 1 node's width of space. So then I can just go 1 more than that. Mesh size of 3 actually gets us pretty close to where we want to be. All right, and you can actually see that this mesh size is pretty close to where we started. Remember, our default was 3.197, and you'll find that a majority of the time, the Moldex3D default for more complicated parts is actually going to be quite accurate to the Goldilocks method. We've done this on purpose, and funnily enough, the more complex your geometry gets, the more accurate the default is. And the reason for that is because the more feature lines this function has to go off of, the more information we have to create a good average and to recommend a good default mesh size setting. If I were to mesh just like a box with only 6 surfaces, that only gives me 12 feature lines to go off of. And those 12 feature lines are not really enough to give me a good definition of mesh size, right? I need a good number of data points in order to achieve a reasonable mesh size. All right, so it's just something to keep in mind. A lot of times for more complex geometries, the default will actually be quite accurate, but regardless, I always recommend to come into the modify node seeding function and apply this Goldilocks method yourself so that you can get the highest quality mesh while kind of decreasing your computation time as well. All right, so I'm going to go ahead and press the green check mark once I'm satisfied with my node seeding. And this will send me into what's called manual node seeding. So what we just did is we set the same node seeding to every feature line of my geometry in what we call a global node seeding. Now we can actually come in and start manually specifying the mesh size on the different feature lines across my geometry. Where this is particularly useful is small features that are in the middle of a surface. So things like ribs, things like bosses in particular, these sorts of circular objects are are very important to pay attention to because if you look at the inner the inner diameter, I guess, of this boss, you can see that although we have applied a really good mesh size for the rest of the part geometry, that only leaves 6 nodes around the circumference of the inner diameter of this boss. When we go to convert this to a series of triangles, it means that this is going to become a hexagon, right? And that's not really a good approximation of this feature. If I'm actually really concerned with this feature, if that's the whole purpose I'm running the simulation is to see how this fills out, I'm not really going to get a good mesh resolution in there. All right, so that's where the manual node seeding really comes into play. I can actually just do a left click drag box select and select all the feature lines across that boss. And then I can decrease the mesh size
of all of those feature lines simultaneously from an average of 2.5 to maybe an average of 1. You'll note that we had a surface mesh size of 3, and we saw the average mesh size was 2.5. So that just kind of hits home what I was mentioning before, that not every feature line set will have um, the same global setting of 3 that we had before. All right, so once we set to the mesh size to 1, you can go ahead and press enter. And then if you left click off in space, you can really see the difference between the new node seating on this boss versus the old node seating if you contrast that to one of the other bosses. Now feel free to apply this setting to the other bosses as well. I'm going to keep the mesh as is right now, or I'm going to keep the seating as it is right now, just to contrast these two when the surface mesh actually gets generated. All right, we can go ahead and press the green check mark, and now we get to move on to the solid mesh. So now that we have a good quality surface mesh, we can go ahead and look at the parameters for the solid mesh. Note that we haven't actually generated the surface mesh yet. But before I go too far into meshing the actual system here, I want to explain a little bit more about how Moldex3D handles boundary layer meshing. And for those of you that are unfamiliar, this will be a good lesson to know how boundary layer meshes are generated. All right, so to know what I'm talking about, you can go ahead and start in the parameter function. And I'm going to show this presentation. All right. So every surface set on your geometry has an upper and lower bound. So in every location of your geometry, you have either an upper and lower surface, a left and right surface, a front and back surface, whatever you want to consider it. You always have an upper and lower bound. What we just did in the node seating was we put a bunch of nodes across the upper bound and the lower bound. That creates our surface mesh. The surface mesh nodes are then going to be extruded from the top side downwards and from the bottom side upwards to create a 3-layer structure. The top and bottom layers are going to be called the boundary layers. That's where BLM gets its name from, boundary layer mesh. And then the middle layer is actually going to be slightly different. We call it the tetrahedral layer, or the tetra layer for short. Now the boundary layer mesh, if we kept it as is, as just one single extrusion, we wouldn't really have enough resolution to give us the result outputs that we need to discern certain phenomena throughout our part geometry, through the thickness of our geometry. One of one of the main purposes of using solid mesh is so that we can break open the part and see what's actually going on through the thickness. So we want to be able to capture all of those results in a higher resolution. And for that reason, we always segment our boundary layers into a series of sub layers. In most cases, we're going to use what's called a 5 layers BLM. And if you look in the interface, you'll see that that's one of the first things that you see. You see the mesh type, and we want to set that to 5 layers BLM, which happens to be the maximum that we can set to. All right, 5 layers BLM gives us a total of 11 layers through the thickness. We have 5 on the top, 5 on the bottom, and at least 1 layer of tetrahedral mesh through the middle of our thickness here. And what this tetrahedral layer is meant to do is to connect the two boundary layer meshes together. Unfortunately, the nodes on the bottom side of our part and the top side of our part, as we're looking at it here, will never line up with one another. If we were able to get these nodes to line up with one another, then we could just extrude the mesh all the way through the thickness to create an extremely high quality mesh called a hybrid mesh. But unfortunately, because the nodes on the top side and the nodes on the bottom side don't line up, we'll create what's called this boundary layer mesh where we have a tetra layer in the middle that acts as a connector. Now there's two main types of mesh that we use in the boundary layer meshing, but there's actually three different types of meshing in total that we have in Moldex3D. The first meshing type is called, or the first mesh element type is called a tetrahedral element, or tetra for short, and that's obviously what we use in the tetra layer. This is a four-sided triangular element. And the reason that we use this type of element is because it's very flexible. I can pull any of these corners however I want to. This element is very, very flexible, meaning that it's able to conform to the extrusions that the two boundary layers give us. The next type of element is a prism element. It's just an extruded triangle, which is exactly what we have. Remember, our surface mesh is triangular in nature, and we're just extruding that to create our boundary layer section. So prism elements are what we actually use for the boundary layers. Prism elements in general are much more structurally rigid because of the quadrilaterals that are created on the sides. So these prism elements are a little bit more structurally rigid, making them not ideal for something like a structural analysis where you actually need to deform the mesh. For that type of analysis, usually you want tetrahedral elements so that the mesh is a little bit more flexible and more deformable. But prism elements give us a fantastic resolution for flow analysis, which is the primary reason that we use them. The last type of element that does not appear in the boundary layer mesh is called a hexahedral element. A hexahedral element, you can think of it like two prism elements put together. It's instead of a triangular element extruded, it's a quadrilateral element extruded. All right, so if we were able to create a quadrilateral surface mesh and extrude that instead, we would create even a higher quality element, which is called the hexahedral element. Now, I just mentioned the quality of the elements. Actually, the quality of the elements is determined by the number of nodes where the computation is actually done. So there's going to be computation done on all four of these nodes, for example, for a tetrahedral element. And then the computation for those four nodes is going to be interpolated to the middle of the element where the results are stored. The more nodes you have, the more computations are done, the more resolution, or really the more precise the results are going to be. All right, so for a tetrahedral element, you have four nodes. For a prism element, if you just count the corners, you have six. And for hexahedral, yeah, you probably guessed it, we have 8 nodes. So hexahedral elements are always going to be the highest quality simulation element as far as flow analysis is concerned, followed by prism, and then followed by tetrahedral. That's not necessarily to say that tetrahedral elements are bad quality. They're just the lowest quality as far as computation is concerned. But actually, you might notice something kind of weird. We put the tetrahedral elements, which are the lowest quality elements of the ones that I mentioned, right in the middle of our mesh. And you might think to yourself, is that actually going to be a problem computationally? Let's take a look at this. All right, so we'll use the injection molding velocity profile. You could use a temperature profile, pressure profile. A lot of the profiles in molding follow a similar type of trend. But the velocity profile, as we all know, plastic exhibits fountain flow, so it's the easiest to understand. It's just parabolic where the maximum velocity is in the middle of our mesh, and then the velocity is pretty much zero right at the surface of the mold. So you might think, well, isn't the velocity the max in the middle of our mesh where our tetrahedral mesh is? Isn't that a problem? Well, the answer to that is actually no, because the impact of the elements is not necessarily dependent on the magnitude of the results being output. It's the gradient of the results being output. And gradient is just a fancy term for the change in the results across that profile. All right, so if we draw a little arrow down to where the profile contacts the tetrahedral layer boundary, we actually see that the change in velocity across the thickness of this layer is very small with respect to the change in velocity across the boundary layer, right? And that's the whole reason, that's the whole philosophy behind the boundary layer mesh, is that the higher quality mesh is out where the results being obtained are have a higher gradient or are a little bit more interesting. The slope of this profile is almost zero in the tetrahedral layer, which means that the impact of these tetrahedral elements are actually going to be quite low with respect to the impact of the prism elements in the boundary layer. All right, the other parameter here that we have to pay attention to is what we call the boundary layer offset ratio. And up until now, I've really just kind of given a diagram where we have 3 layers, but I haven't really defined how the thickness of these layers are defined in Moldex3D. All right, we define the thickness of each of these layers with what we call the boundary layer offset ratio. The boundary layer offset ratio, you can actually see this in the interface, is governed by the equation T equals S times OR, where T is the boundary layer offset distance, or the thickness of the boundary layer. S is the mesh edge length, or the node seating, you can think of it as. And then OR is simply this parameter, this scalar parameter, which we call the offset ratio. So if we break this equation down numerically, what we can see is that as we increase the offset ratio, we increase the boundary layer offset distance because they're proportional to one another. All right, that's really what you need to know. We're not ever going to change the node seating to impact our boundary layer offset distance. This is more of just a constant. You can almost think of it as. All right, so based on this equation, let's see the impact of the boundary layer offset ratio on our mesh quality. All right, if we have a low offset ratio, that means that our boundary layer offset distance, our boundary layer thickness, is going to be quite low. And that means that the space filled in between the 2 boundary layers increases. Obviously, that's the tetrahedral layer, which means that the tetrahedral layer starts having more of an impact on our results because it's capturing more of the gradient of our profile. We want to avoid this. And the reason for that is really, just as I mentioned before, we want the tetrahedral layer to have as minimal of an impact as possible because the boundary layers, because the prism elements are able to capture the gradient at a little bit higher resolution. On the opposite side, if we make the boundary layer offset ratio too high, then theoretically, we could have boundary layers that are greater than half the thickness of the part, which means that they would overlap one another. This is a simulation no-no. We can't have 2 elements in the same geometric location. That would cause a divergence in the simulation almost immediately. But luckily, this isn't something we really have to worry about. It's something that we had to worry about in the past, but not anymore. And the reason for that is because Moldex3D has implemented an algorithm into their boundary layer meshing kernel that allows us to dial back the boundary layer thickness if it is recognized that the boundary layer thickness is greater than half the thickness of the part. So essentially what that means is if we are to have overlapping mesh, Moldex3D is going to automatically recognize that and reduce the size of reduce the thickness of the boundary layer so that there's a minimum tetra layer through the middle, something like this. Which, if you compare that to what we've been looking at the whole time, this is actually our ideal BLM. We want to make sure that the tetrahedral layer has as low of an impact as possible, but we still actually want this to have some relative thickness to it, just to make sure that the elements are good quality. All right, so this ends up being our ideal BLM, and we can actually take advantage of this in the interface because we know we can be confident that there's never going to be overlapping mesh, which means that we can set this offset ratio as high as possible and then let Moldex3D take over to create that minimum tetra layer in the middle of our thickness. So what it boils down to simply is we're going to be using a 5 layers BLM with a maximum offset ratio of 3.0. If I try to set this any higher, you'll see that we find the constraints are 0.1 and 3. All right, so 3.0 is you don't have to set this every time. Once you create a mesh in Moldex3D, these parameters get saved as the new default. So next time you come to create a mesh, these will be the new defaults, and these are the best practices for every mesh that you want to use. All right, so that does it for geometry meshing. Now we get to move on to the other type of meshing that we have, which is called curve meshing. Curve meshing will be used for any line-defined object. Remember, we have two different types of line-defined objects in our model currently. We have the gate and we have the cooling channels. The reason that I recommend line-defined elements over CAD geometries is specifically because of how we handle the solid mesh for line-defined objects. What we're going to do is we're going to define a two-dimensional template, which is going to be pasted onto the inlet. And then that template is going to be extruded along the line. Now, if you remember from that presentation I just showed, we have a pure quadrilateral surface mesh template here that we're extruding. So that actually creates hexahedral elements, which are the highest quality element possible in simulation. All right, so we get a very high quality mesh, and it's also going to be perfectly consistent because this template is essentially just going to be extruded and then divided a certain amount of times to retain the quality of the mesh. The same thing goes for the cooling channels. If you click on this little drop down here, you can go to cooling channels and you can define that template a little bit differently as well. If you're doing a CFD study, for example, or a computational fluid dynamics study, then you may want to increase the number of layers towards the surface to capture the velocity gradient a little bit better. However, if you're just doing a molding analysis, then this sort of template is perfectly fine. Actually, both of these templates are perfectly fine. The defaults are customized to our best practices, and you should be able to just come in here every time you from this point forward. Once we generate the mesh for this model, you really shouldn't have to come back into the solid mesh. The solid mesh parameters, they'll be set the same for every geometry that you run through Moldex3D. All right, so you can go ahead and press the green check mark to get out of the solid mesh parameters, and then we're going to go ahead and generate the entire mesh. All right, so we're going to go into generate, and this time we're actually going to go ahead to the bottom where it says generate. We'll click that, and it'll begin the meshing process, starting with the surface mesh of the part. And you can actually see that, just like I described earlier, the solid mesh or the surface mesh of the part is literally just taking every surface on our geometry and converting it to a series of triangles. If we look at the bottom where we refined that boss and contrast those two, you can see that this boss is much more, much better defined than this guy over here. You can see that hexagon that I was referring to earlier. All right, so next it's going to create the solid mesh of the part, which we're not really going to be able to see. The boundary layer mesh is going to be inside of the surface mesh, so we won't be able to see that. We'll slice through it in just a moment so you can see what that actually looks like, but you won't see anything right now. Then it's going to generate the solid mesh of the runner. And the cool thing is you can actually see that two-dimensional template that I was just referring to earlier, and that's going to be extruded along the line to create those hexahedral elements. And then that template is actually going to be pasted onto the part to create a perfect match between the gate and the part geometry. And it creates a one-to-one translation, a very fluid propagation of the data from your runner system into your part. Very, very important that we have a match there. All right, next it creates the cooling channel solid mesh. This is just an extrusion of that two-dimensional template once again. And then finally, it's going to create the solid mesh of our entire mold. The mesh type that's going to use for our mold base is tetrahedral, just like we had for the middle of our boundary layer mesh. And the reason we use tetrahedral mesh is because, once again, it's a little bit more flexible, and the mold base needs to conform to every object in our modeling window here. So we need to have a nice flexible mesh that's going to be able to handle the heat transfer. And as it turns out, tetrahedral elements are actually quite efficient at heat transfer. All right, so we should see the mold base pop up in just a few moments here. There it is. You can see it's just a big old box. And again, there is no parting line. As you can see, there's no parting line. We don't actually separate the cavity and core sides of our mold. And before we export our mold, you can go ahead and click Final Check and just kind of follow along with me visually here. You can go ahead and click this Final Check button. Or if you'd like to, you can also go in and chisel the model along with me. So to chisel, we're actually going to go over to the Tool tab. And over towards the right, we're going to go ahead and click Chisel. And then we're going to left-click drag a box. And any element contained within that box is going to be temporarily hidden. Then I can zoom in to actually just see what kind of mesh was generated. So we can actually see that 5 layers BLM be generated here, 5 on the top, 5 on the bottom, and then our tetrahedral layer through the middle. We see that pure tetrahedral mesh for our mold base. And we have our cooling channels over here. There's these hexahedral elements that are perfectly consistent along the line. All right, very, very high quality mesh. And something that's super important, I can't iterate this enough, is how Moldex3D uses true 3D solid mesh for every object, every simulation object, which gives us the highest precision of results that we can get. All right, you can go ahead and toggle off the chisel if you went in chiseled, and then we can go back to the Mesh tab and click Final Check. Final Check will do 2 things. It'll first of all save our mesh file, and then it will convert the mesh file over to a simulation file. So it'll convert it to something that's actually usable in the Moldex3D simulation. All right, once that file has been saved, you can go ahead and press OK where it says mesh is ready for analysis. And that'll actually shoot you back over to the Home tab. So we were in the Mesh tab. It's going to convert us over to the Home tab, where we can continue on from where we got sent from the Home tab to the Model tab, which was the Import Geometry. I'm going to skip over boundary conditions for now. These get a little bit more complicated than I want to get into here. But if you do have any questions about the boundary conditions specifically, feel free to ask those in the chat. All right, moving on to the right of that. Again, we're just going from left to right across the interface, which is really quite fantastic. It allows us to streamline this process quite easily. All right, so we're going to go ahead and click Material. And this is going to allow us to select the polymer that we're going to be injecting into our model. Now this works for thermoplastics, this works for thermosets. There are a bunch of different types of simulations that you can run in Moldex3D, and we actually have our own database for materials. If you click on the dropdown where it says not specified, for new installations, you'll just see 2 options for Material Wizard and Import. But if you've run a couple of simulations in the past, you might see some recently used. You might have already added materials to your user bank, which is really just more of a kind of like a short list of materials that you might use on a more regular basis. But for this case, we're going to go into the Material Wizard. All right, and the Material Wizard on the left side has 3 tabs. The blue Project tab should currently be blank. Reason being, we haven't selected any materials for our project quite yet. The green User Bank tab Like I mentioned earlier, it's going to be kind of like a short list of materials that you might use on a more regular basis. So if you know your company uses a certain material quite often, then you might want to add that to your user bank instead of having to go through our database every time. Speaking of the database, the red Moldex3D bank tab is Moldex3D's material database, which currently sits at just over 9,000 materials. So you should be able to find what you need a majority of the time, but we do have a couple of other options if you can't find your material in our database as well. All right, so just as from an organizational standpoint, we start with the polymer type. I'll just use ABS here. Then then the subcategory is manufacturer. I'm just going to use the first one, and then the grade name. All right, so that's how our database is organized. You can actually use the browse function as well if you want to find your material a little bit faster. You can go up to material find or use the shortcut Control F to open up the browse function, and then you can search for a certain polymer, a certain producer, and if you're using a grade name, make sure to press this little checkbox over here, and you can search for the grade name, and it'll give you all of the options within that specified criteria. In addition to this, you can click the little arrows over here on the bottom right corner, and you have access to more advanced search criteria, more just material properties, things like your MFI, the density, filler content, and processing windows. So if you want to search for a material, you can certainly do so that way as well. Now, if you don't have, if Moldex3D doesn't have your specific material grade in our database, you have really three main options for obtaining material data to run in your simulation. The first and by far the most popular thing to do is to just send Moldex3D the spec sheet. You can just email us the spec sheet of the material. And from that, our material lab over in our headquarters in Taiwan will actually help us to, the material experts there will help us to suggest a material for you to use in your simulation. All right, so if you don't know what material to use, you can just send us the spec sheet and we'll recommend one for you to use that's similar to that. The second option is to obtain the raw data from a material testing. So whether your company has outsourced the material testing, or maybe if the material supplier has done their own material testing for that grade, you can obtain that raw data and we can fit that to our numerical models. All you have to do is send us the raw data and we'll give you the material file back for use in Moldex3D. And then the third option, probably the best option, is to get your material tested by Moldex3D. Obviously, since we're the ones kind of curve fitting a lot of these material files, getting your material physically tested by us is actually going to be the best way to get a material file into your database. So we do have the capability to do that. Like I mentioned, we have a material lab over in our headquarters where we can actually do this sort of material testing. We have all of the applicable equipment, things like PVT machines, rheometers, thermal properties, mechanical, things like a tensile machine, all those sorts of things we have to characterize the material for use in Moldex3D simulation. All right, so those are your three options. If you don't see the material in your database, we can recommend an alternate. We can convert a material testing raw data set, or we can test the material for you. All right, if you do have any questions about that, feel free to show those in the chat. But otherwise, we're just going to add this first material in the database by right-clicking on it and clicking Add to Project. When you do so, it's going to come up with a little prompt that asks you if you really want to add to your project. And then it's going to ask me to add the material to my user bank if I haven't done so already. I'm going to click No. But you can feel free to add that material to your user bank if you want. Just to double check, we can go to the project tab and we should see that that material is successfully loaded into our project. And if it is, we can just close out of the material wizard. We should see that that's automatically loaded as our material. And then from there, you should see all of the buttons across the top start to light up. Moving on from the material, we get into the process. I unfortunately don't have a whole lot of time to get into the process. If you have specific questions about the process, feel free to shoot those into the chat. But as far as the process wizard goes, when you first install Moldex3D, you're going to start off in simple mode, which gives you access to kind of a select few parameters. You have filling time, packing time, cooling time. You have your processing temperatures, and then you have your machine's maximum pressure. All right, so those are actually a pretty good place to get started using Moldex3D. But if you want to get a little bit more specific as far as the process, then you can change from simple mode by going to the option down here at the bottom left. You can change from simple mode to classic mode, and that will give you some more options. So we can see the filling time, but we have things like your flow rate profile. You can see the packing time, but you have the ability to input your packing pressure, specify a VP switchover, a lot more options as far as the processing is concerned. All right, like I said, I don't have a whole lot of time to go through the process wizard here, but if you do have any specific questions about the process, what parameters we can define, is there a certain parameter that we can consider in Moldex3D from reality? Those sorts of questions, you can ask those into the chat. But otherwise, I'm just going to go ahead and click cancel so that I can retain the default process that's created for me. If you don't have a whole lot of knowledge about processing in general, Moldex3D will give you a very valid process by default. We've actually put in a lot of work recently to get the default process as close to or as reasonable as possible. Obviously, there's going to be minor tweaks that you're always going to do between what the Moldex3D gives you and what is actually done in reality. So you can always apply those, but if you don't have that information, you can definitely use the default process if you want as a starting point. Moving on to the right of the process, we get into the analysis. This dropdown allows us to select the sequence that Moldex3D is going to use for the analysis. And there's 4 main sequences that are really used on a common basis. The first of which is what we call quick flow. Quick flow, just as the name might suggest, is a very fast analysis, but only for the flow of the material through our geometry. This analysis actually kind of neglects a lot of the viscous parameters of the material, which might sound ridiculous, but it actually allows us to get a pretty reasonable visualization of how the material is going to propagate through my geometry. So if you're just trying to define a gate location, using the quick flow, I can get my results in maybe 30 seconds, maybe even less than that. I can see how the material is propagating through my geometry. Is my end of fill regions filling out simultaneously? If not, I can make a change to my gate location, run the quick flow analysis again, and I can actually churn out a full gate location study using quick flow in a matter of minutes, which is actually quite impactful when it comes to saving time in the design stage. Once I've arrived at my gate location, then I can actually run a real filling analysis. The real filling analysis will actually consider the viscosity of the material. You'll be able to see all of the results that you would expect, things like temperature, pressure, viscosity, all of the results that you would expect out of a molding simulation you'll get out of the filling analysis. And then from there, you can actually get a little bit more comprehensive with a filling and packing analysis, the third analysis type that we typically use. This allows us to see the packing effect of the gate. You'll be able to see your volumetric shrinkage distribution. You'll be able to see your packing pressure distribution and all that good stuff. So this allows you to really hone in your filling and packing process. And again, if you're just running filling and packing, you don't really need a cooling system. But once you move on to the last type of analysis, which is what we call a warpage analysis, or what is defined in here as a transient analysis 3. Once you move on to a transient analysis 3, you need a cooling system. If you don't have a cooling system, you actually can't even run this. It'll just say fill, pack, warp, which means that we're foregoing the entire cooling part of our cycle, which obviously is not realistic either. So we want to make sure that we have a cooling system input in order to run this transient analysis 3. The sequence itself goes cooling, fill, pack, cooling, warpage. The initial cooling gives us a temperature distribution, which is an input into our filling and packing. So this cooling distribution, or the temperature distribution in our mold base, will marginally impact what happens in the filling and packing stages. So your analysis does get slightly more accurate if you run a cooling before the filling and packing. The second cooling is really just an update of the first cooling based on what actually happened in the filling and packing. There's a couple of assumptions made going into the first cooling, but the second cooling really removes those assumptions based on what actually happened in the filling and packing. And then finally, we take our part all the way down to room temperature in the warpage analysis. All right, so we eject our part, we cool all the way down to room temperature and see what is the difference in shape between our initial model and our final output model. All right, so those are the 4 analyses that are typically run. We have the quick flow analysis, FQ, we have filling, F, and then we have filling and packing, FP. We have our transient analysis 3, which is CTFP, CTW. All right, so those are the 4 analyses that you should consider. Anything else in this list you can pretty much just forget about, as they're really just remnants of the past at this point. All right, moving on to the right of analysis, we're going to go into computation, and we've actually put, kind of similar to what I mentioned in the process, we've put in a lot of effort to make these inputs as accurate as possible to our best practices. There's just a couple of notes that I want to make here, and the first of those is actually under the flow pack tab towards the bottom, where we have this little table. The first thing in this table is what we call the time step output setting. Time steps are an intermediate output of the results from Moldex3D simulation. So if you wanted to, maybe if I have a filling time of 0.1 seconds and I want to see what's going on at half the filling, maybe I want to see the temperature distribution at 50% fill, I can go back to 0.05 seconds and see what's actually going on as far as the melt temperature. This also applies to the packing stage as well. If I want to identify things like gate freeze, which is a very common simulation tactic, time steps really help you to go back into the packing stage to see where the molten material actually lies, and is there a connection between the molten material in the gate and the molten material in the part. All right, so increasing your time steps really just gives you a higher resolution of these time step outputs. I recommend 10 for each of the filling and packing. You can go more. Note that if you go too high, if you start increasing this too much, it can actually start to impact your total simulation time. These take usually, on average, about 30 seconds to output. So you can see how that might impact your results if you increase this too much. But 10 time step outputs is really a good enough resolution for you. You can modify these by simply just highlighting either of them and go to edit, and you can just change this value here. You can just scroll down and change the other one as well. All right, the only other change that I want to mention is over in the Cool tab, and it's right at the top where it says Cooling Channel Analysis By. There's 3 types of analyses that you can run as far as the cooling is concerned. If you uncheck this box, which I believe is the default, we're going to be running what's called a heat sink analysis. A heat sink analysis means that the cooling channels are acting as a conduction object, And then there's some assumption of flow through that conduction object to create a heat transfer coefficient. Now, that is accurate to some degree, but unfortunately, it doesn't give us a realistic definition of the flow through our cooling channel. All right, so although it does make the simulation marginally quicker, I do recommend to check this box and run what we call a cooling channel network analysis. This will give us a temperature distribution through our cooling channels. This will give us a pressure distribution through our cooling channels, velocity, that all that sorts of stuff, with the exception of maybe fully characterizing the cooling channel flow, which is what we do in our 3D solid cooling channel analysis. The third type of cooling channel analysis we can do. Run 3D solid cooling channel analysis is a full CFD study through the cooling channels. If you're interested in that sort of thing, it gives you streamlines, it characterizes the flow, giving you your Reynolds number distribution, gives you your velocity gradients, all that sorts of stuff that you might be interested in. As you might expect, this CFD analysis takes significantly longer than a regular cooling analysis, so I don't recommend to run this unless you're specifically looking at characterizing the flow through the cooling channels. All right, for most analyses, I recommend to use the kind of like the intermediate option, if you will, or the middle option, which is run cooling channel network analysis. Just check this box. All right, from here, all we have to do is click on the template setting all the way at the bottom left corner, and you just check the box that says save current setting as default, and then you don't have to worry about changing these parameters ever again. Kind of similar to what I mentioned in the meshing, this will save these parameters for the next simulation that you set up, so you don't have to come in here every time. All right, so from here you can go ahead and press OK. And at this point, we are all set to run our analysis. Now, I don't recommend to run the analysis right now just because we're going to be getting into post-processing right after the break here. And it will chew up some of your computer's resources if you run the analysis right now. But feel free to run the analysis after this training is completed so you can see some of the results yourself, or you can complete an analysis all on your own. All right, but from here, we are going to be taking about a 5-minute break once again. And when we come back, we're going to be talking all about post-processing and how we interpret some of the results coming out of the simulation once we've run it. How do we actually qualify those results, and how do we use those in a meaningful way to make changes or to see what's going on in the molding process? As always, just make sure if you do have any questions, you can shoot those into the chat. We'll have one small announcement before we get started again. All right, before we get started into the last section, I just wanted to mention to everybody that we do have a YouTube channel, quite new, Moldex3D North America. Feel free to go and check that out. We have a lot of nice advanced tutorials and a lot of information that you can use to quite good benefit. If you it's a lot of our trainings, a lot of our best practice guides, all that sorts of stuff. If you want to go and check that out for specific topics, feel free to do so. We even have a nice little quick start tutorial right on the front page here. It's just like a 5-minute video to get you started, or just as a refresher from this session. So definitely feel free to check that out. You can even subscribe to Moldex3D North America. It doesn't cost you anything. Just gives you notifications when we upload new videos, which we do quite regularly. So feel free to go and check that out. But without any further ado, let's jump back into Moldex3D. And actually, we're going to close out of the current session. And we're actually going to go ahead and open up the pre-run simulation that I gave you, which should be in the consumer folder. All right, so you can go into the consumer folder and you should see just an M3J file. We won't do anything with that quite yet. We're actually going to use Moldex3D to open up that M3J file. So we're going to go and open up a new instance of Moldex3D Studio 2020. Or whatever version you have installed, if you have an older version. All right, and instead of clicking new like we did at the beginning, we're going to go ahead and click open. All right, and we're going to route to the consumer folder. And most of you guys won't have the MRM file. MRM is typically the file type that we use to open up these sorts of projects. However, in this case, we only have the M3J, which if you've been working in the older interface, then you might actually only have M3J files from the older interface, and you'll need to open those up in Studio. We can do that if you change the file type from MRM to M3J. You'll be able to open up those older M3J files in Studio. And we'll be able to see the pre-run simulation here. All right, so over in our project tree on the left side, you'll see that there are 4 main results sections. We have filling, packing, cooling, and warpage. Remember, our analysis sequence was CT, FP, CTW. The second CT overwrites the information from the first CT, so we're just left with filling, packing, cooling, and warpage. All right, before we go too far here, I do want to note one thing. We typically like to get rid of the mesh lines when it comes to result interpretation. The reason being simply they get in the way. It's a little bit difficult to see the contours of the colors when the mesh lines are here. So we're going to go up to this little toolbar up in the top middle of our interface. We're going to click on the drop down next to the box. It looks like maybe like an orthographic box with some mesh lines. And click on the drop down, go to the third option, which says show feature lines with shaded faces. I'll simply just get rid of the mesh lines. All right, and we're going to go into the filling results to start off here. And when you go into the filling results, you'll also want to be in the result tab. And actually, if you're back in the home tab, there is and funnily enough, to the right of the run function, remember that left to right philosophy, to the right of the run function is the result button. So if you wanted to keep that philosophy going, you could click on the result button, or you could click on the result tab directly. Either works. All right, so the first result that shows up in filling is the melt front time, and is one of the most important results that we get out of molding simulation. Simply said, this contour plot shows us how long the material has been in the part, or how long since the material left the melt entrance. All right, so blue represents the longest time, red represents pretty much the melt entrance. So it really just kind of shows us how long it took to get from the melt entrance to that location. But the color contour doesn't really give us a whole lot of information. What we're more interested in is the animation. So we're going to go ahead into the animation section of our result ribbon. We're going to just press play, and that'll give us an animation of our flow progression. And now there's a couple of things that I usually look for when it comes to the flow animation here. And the first one is what we call flow balance. Flow balance is essentially just trying to get every one of our end of fill regions to fill out simultaneously. And we want to do this for two reasons. First of all, if we're able to get all of the end of fill regions to fill out simultaneously, we are optimizing our flow length. The reason we want to optimize our flow length is to reduce the pressure required to fill the part. Let's break this down a little bit. As the material propagates through our geometry, more pressure is required to retain the constant flow rate condition. So during the filling stage, we're trying to maintain a constant flow rate. And as the material progresses through our part, more resistance is generated to flowing. So we have to apply more pressure from the melt entrance to keep that material flowing at a constant speed. The longer the flow length, the more pressure drop is going to occur through our geometry. All right, so for example, if I were to put my gate over here, my flow length to this side of my geometry is actually going to be quite short, which is fantastic because the pressure drop is going to be pretty low. But then we sacrifice this side, right? The flow length to this side is going to be much longer. And that will create an overall increase in pressure to fill our geometry. If I can place my gate such that both of my end of fills fill simultaneously, it means that my flow length is optimized, which means that ultimately the pressure requirement for the part is optimized as well. The second reason, and maybe arguably the more important reason, is because of what we call pressure spikes. Pressure spikes occur because of a momentum shift of the material from one region to another. To identify this or to visualize this a little bit better, we're going to look at a result called the sprue pressure plot. So if you scroll all the way down to the bottom of your filling results, where it says XY curve, the first XY curve that shows up is your sprue pressure plot. And like I was mentioning before, this is kind of the pressure resistance to maintain that constant flow condition that I was mentioning earlier. Right. So as the material flows through the part, more resistance is created, which means the pressure has to constantly increase in order to maintain that constant flow condition. But if there is a disturbance in the flow, like what we see right here in the middle, we get what's called a pressure spike. So let's back up our animation. You can actually use this little slider up in the animation toolbar. You can use this slider to move your animation back and forth, and you can see that dotted line move across the graph as well. We're going to go just before this pressure spike occurs to see what exactly is happening at that point that might be a little bit abnormal. I'll save you a little bit of time. If you go up to the top right corner of your part, we can see that this corner is filling out. And what ends up happening is the material, when the material begins to flow, or when the material develops its flow, it really has three choices, right? You can either go to the left side, you can go to the top right side, or you can go to the bottom right side. The material that goes up toward the top right side, once this fill is completed, once there's no more volume to fill, the momentum of the material going in that direction has to shift to either going towards the left side of the part or towards the bottom right side of the part. This momentum shift, if it occurs through the gate, which in this case obviously it does, will create a little bit of a pressure spike. Now, the cool thing is, if this imbalance happens in the middle of our flow, it doesn't actually end up impacting our pressure too much. However, if the pressure imbalance happens close to the end of fill, the main end of fills, like this guy over here and this guy over here, if these two are imbalanced, then you can actually get a pressure spike right at the VP switch point, which is where this peak occurs. You can get a pressure spike right close to this VP switch point. That pressure spike is going to be very sensitive. It's going to be high in magnitude, and it can end up hurting your machine. So you want to avoid having any sort of imbalance close to your VP switch point. All right, so let's close out of this graph real quick to give a little bit more attention to how we identify flow imbalance. All right, you can go up to the top right corner of the graph to close out of it. And now I just mentioned that we want to make sure that that our flow is balanced, but how do we define balanced? Well, what that means is we want every one of our end of fill regions, our major end of fill regions, so kind of neglecting this guy up here, just considering maybe the left side and the bottom right corner of this part. We want our end of fill regions to fill out after the VP switch point. Once the VP switch point is reached, we are then transitioning our pressure to a constant pressure condition for the packing stage, and then pressure spikes really aren't allowed to occur at that point. All right, so what I'm going to do is I'm going to I'm going to turn my melt animation to my VP switch point, which in this case was 95%. I switched over at 95% volume filled. And what I want to see at 95% is that both end of fill regions are unfilled. I want to see that both end of fill regions are still filling out. And the further I can push this value, let's say I go to 98%, the further I can push this value and still see that both end of fills are not completely filled yet, the more balanced my fill is. Now, like I said, anything after the VP switch really doesn't matter, but the more balanced you can get, the more optimized your flow length, the more optimized your pressure. So, so it's never a bad thing to be able to go a little bit later than your VP switch as far as the flow balance. All right, the other result that I like to look at in the filling stage is the filling temperature. The filling temperature gives us an idea of what's actually happening with the plastic as it flows through our geometry. Because plastic is viscous, it exhibits a shear heating effect. Shear heating meaning that the individual polymer chains will actually rub up against one another and create friction. That friction increases their heat and creates kind of a secondary heating source as the material flows through our geometry. So the filling temperature result allows us to see the impact of that shear heating, as we call it, through our geometry. And there's two main effects that are going to combat one another when it comes to the temperature result here. There's the cooling effect. As the material flows, the heat is going to be dissipated into the mold. But also, like I just mentioned, as the material flows through our geometry, we're creating, friction is created as the moving material rubs up against the frozen material closer to the mold surface. And that actually is a secondary heating source. So the temperature result allows us to see which effect is dominating. Is the cooling effect dominating, or is the shear effect dominating? If the cooling effect dominates, what will happen is the temperature will be highest at the melt entrance or at the gate region of our part. If the shear effect dominates, then the highest temperature will be at the end of fill. Just looking at the surface temperature doesn't give us a good depiction of what's happening through the thickness. That's one of the main advantages of using 3D solid mesh is we're able to actually look at what's happening in the middle or in the center of our part. All right, so we're actually going to use a nice result interpretation tool to look at what's happening in the middle. It's called the isosurface tool. The isosurface tool allows us to remove every number except for the one that is shown here. All right, so every color except for that which represents 179.967 plus or minus maybe some sort of tolerance. That's what's shown here. Now I want to see where the hottest material is in my part. So I can actually move this slider towards the hotter side of my scale or towards the right side. And that really allows me to see a good depiction of where the hottest material lies in my part geometry. All right, so we can see pretty obviously that the material is hottest at the end of fill regions, which, as I just mentioned before, indicates that shear heating is going to dominate the cooling effect. All right, so let's see the impact of this temperature distribution on our packing analysis. All right, so let's jump into the packing results. The first thing I'm going to look at is packing pressure. You can get out the isosurface tool. We're just going to look at the color contour. All right, so packing pressure. And you can immediately see that in this simulation, the packing pressure is quite concentrated around the gate region. The thing to note about the packing stage, or the whole purpose of the packing stage, is to continue injecting material into our part geometry to combat the natural effects of material shrinkage. So we are stuffing more and more material, increasing the density of our part so that our part doesn't shrink as much. But that packing effect can only be distributed through molten material. Once material is frozen, we can no longer pack beyond that region. And that's typically why you see a concentration like this. Usually it means that a majority of your part, or pretty much all of the part in most cases, is frozen except for your gate region, which is a good indication sometimes that you've packed too long. Now let's take a look closer and see why we have this distribution of pressure. Like I just mentioned, pressure can only distribute through molten material, so it's very useful to see where the molten material lies in our geometry. I'm going to show off a couple of functions here, the first of which is the compare tool. Compare allows us to break our window into two halves. So in the left half, I'm going to have packing pressure. I'm going to left click on the right half to make it my active. I'm going to switch to the result called molten core. All right, from here, I'm going to sync the angle. So if you go to the next to compare and sync the angle, it means that when I rotate one, it's going to rotate both of them at the same time. And we can see that, in fact, at this moment in time, The gate is actually quite isolated, even though we see that there is quite a bit of molten material left over. The gate region is isolated because there's frozen material surrounding the gate region, right? There's no connection really. I mean, I guess there's this little bridge here, but there's not really a solid connection between the gate region and the end of fill regions. And the reason for this, and really the reason why we hate shear dominated flow, like we just saw in the filling stage, remember we had the shear effect dominating. The reason we don't like shear dominated flow is because the material at the end of fill is going to be hot due to the shear heating. The material at the gate is going to be hot because that's where the material is coming from. But there's nothing heating the intermediate region, right? There's nothing keeping the material in the middle region of our part molten, and therefore it freezes off, leaving the end of fill region hot and unpacked, and allowing the gate region to, in some cases, overpack because we're anticipating that um, we're able to distribute that pressure throughout our geometry. All right, so this compare tool, really nice for comparing two results side by side. You can actually do this with multiple runs as well. So if I have run 1 and run 2, I can have the same results open on both runs, and that would allow me to compare them side by side. Very great for creating report screenshots and stuff like that. But can also be useful in situations like this where you want to put two results side by side. All right, so actually what ends up happening is our end of fill region gets left out to dry uh, in two aspects, actually. So the material is hot, which means that it's going to shrink at a higher rate. And it's also not packed very well, which also means it's going to shrink at a relatively high rate. So your end of fill regions are going to shrink a lot more than what's happening at the gate region. And at the gate region, we do have hot material, but we're much better packed, which means the material isn't going to shrink as much. And we can see this reflected if we go into the volumetric shrinkage result. And the results are going to be skewed because the material in the core of our geometry in the middle of the thickness, a little bit hotter, therefore it shrinks a little bit more. So we're going to reduce the scale. So we're just looking at more diverse color distribution across our part. And we can really see how different the volumetric shrinkage is between the end of fill and the gate region. It's almost 1.5% different in this case, which is pretty massive. All right, so looking at results like this is very, very useful. Something that might not be very obvious in the molding process, but can be actually quite impactful, or can allow you to make meaningful changes in your process, in your part geometry, and so on, to maybe avoid shear heating or the shear dominated flow in general. All right, moving on to the cooling results here. Moving right along, the first thing I'm going to look at, obviously, cooling is inherently tied with the temperature distribution. So that's the first thing we're going to look at here. The temperature distribution across the surface of our part, or what we call the skin of the part, is going to allow us to identify where we can make improvements to our cooling system. Now, obviously, the center of our part, the core of our part, is a little bit hotter than the surface. So we're going to once again change our scale until a major region on our surface is like an orange or a dark red color. Oh, we see on the bottom side we have a pretty big hotspot down here. All right, so reducing the scale like this allows us to see where the hot spots are across the surface of my part geometry. So it looks like I have two main ones. It looks like I have this one in here. And then if I flip to the bottom side, we have this one along the channel. And it's very important to note where these hotspots occur because any sort of gradient, remember gradient meaning change in a result, any sort of gradient in the temperature across the surface of my part geometry is going to result in a difference in shrinkage. And a difference in shrinkage is the definition of warpage in Moldex3D. So anything that can create a difference in shrinkage, remember like I mentioned with the end of fill being a higher shrinkage than the gate region. Well, the surface temperature across the part here is hotter, which means it's going to shrink more than some of the other regions. The temperature here is hotter, which means it's going to shrink more, which means that it will pull in all of the surfaces around it. So this allows you to build kind of an expectation for what you're going to see in the warpage. And I can't emphasize enough how important it is to look at the filling, packing, and cooling results before you look at the warpage results. I see so many users go straight to the warpage results. They're all gung ho. You know, we finished our warpage analysis. We got some results. We want to look straight at the warpage analysis, and then there's a bunch of questions that's created that are not really answerable. You know, for example, why is the part warping like this? Well, then it's a scavenger hunt. You can't really look at the warpage and start creating questions. You need to look at the filling, packing, and cooling and create questions from there that are answered by the warpage analysis. You don't want to go the other way around because that's just going to create a lot of open-ended questions. That's going to create a lot of confusion. And I've seen so many times where a lot of pretty efficient teams are bogged down by questions created by just looking at the warpage analysis. All right, so I can't emphasize enough how important it is to actually go through the filling, packing, and cooling analyses and actually take a look at those results before looking at the warpage. All right, so it looks like maybe our cooling system can be improved. Maybe I can bring my cooling channels down into this region. Maybe I can bring a cooling channel along this channel of my part. Improvements like that can improve the uniformity of surface temperature across my geometry and will ultimately result in less warpage. All right, so but why is this bad? Why do we not want hotspots on our part surface? Well, the reason, like I just mentioned, is mostly because of warpage. And that warpage really comes from either a gradient across the surface or a gradient from the top surface of our part to the bottom surface of our part. So you can actually see the top surface here is quite hot, whereas the bottom surface is quite cold. Same thing here. Bottom surface is quite hot, top surface is quite cold. That difference in temperature creates a difference in shrinkage, and that difference in shrinkage results in warpage. So we actually have a result that you can look at directly to identify where we have a high difference between the top temperature of our part and the bottom the core temperature of our part and the cavity temperature of our part, if you will. And that result is called the mold temperature difference. All right, mold temperature difference literally just takes the top surface minus the bottom surface temperature, creates an absolute value, and that's the result you see. So this temperature is a difference. So this is one temperature minus the top temperature minus the bottom temperature. And that's the result you see here. So this isn't like an absolute temperature or anything like that. Now, if I reduce my scale to remove some of the obscurities here, things like your bosses, those will usually have a high mold temperature difference inherently because of how thick they are. But if you reduce your scale a little bit, you can really start to see some of the major regions in your geometry start to show up. And really, we want all regions of our geometry, all major regions of our geometry, to have core and cavity temperatures that are within 10 degrees of one another. Anything greater than 10 degrees, that's really where you start seeing a high volumetric shrinkage difference. And that's where you really start to see warpage. All right, so we can actually set the maximum on our scale to that tolerance. I can set the maximum to 10 by just double clicking on the maximum here. I can set that to 10 and then I get a really cool visualization of where I have deficiencies in my part across the surface. All right, so any region that is greater than 10 degrees different from one another, that's what's shown as an uncolored region. Now you need to pair this with your temperature result to know which side is hotter, but we already knew this section here. We saw that this corner was pretty hot, so that's pretty obvious. We saw it in this feature, the bottom channel here was hot. We actually didn't see this guy at all, right? We didn't focus on this at all because it wasn't notable from the temperature. There wasn't any high temperature there. If I go back to my temperature result, you even use the compare tool if you wanted to. You'll note that there isn't really a high temperature here. The reason for the high temperature difference is because the surface temperature on the top side is actually really cold. This is actually an indication that the cooling system is too efficient in this region with respect to what's happening on the bottom side. That can happen. It's not always the case where we're looking at hot spots. Sometimes we're actually looking for cold spots as well. Any region where there's a high mold temperature difference, that's where those are always going to be subjected to potential for warpage. All right, so this result alongside the cooling temperature result really allows you to just qualify your cooling system and kind of see what improvements you can make and where the deficiencies lie, where you can start talking with your mold designer to see how you can improve the part quality. All right, so all of this information so far is leading up to the warpage analysis. And like I mentioned, you always want to go through the filling and packing and cooling before you go into the warpage. But once you have a good foundation set for yourself, once you've gone through the filling, packing, and cooling stages, now we can actually start looking at the warpage. And if you want a little bit more comprehensive of a breakdown of the filling, packing, and cooling results, I definitely recommend you to take a look at our advanced training 2, where we definitely go over that in much higher detail. We actually have what's called a generic Moldex3D workflow for each of the filling, packing, cooling, and warpage to break down the results and really show where the deficiencies might lie, what we can do to improve the quality of our part. All right, with that being said, we're going to jump into the warpage. The main thing we're going to be looking at is total displacement. The color contour here shows us how far each node has moved from its original position to its deformed position. All right, that's what we're really calculating here. Now, you don't actually see the deformation quite yet. The color distribution is just meant to represent the displacement. But if we go into the deformation function, we actually get to see a visualization of that deformation. All right, and you can scale this deformation if you want to make it a little bit more obvious, but the color here, maybe like 0.97, is the distance between the original mesh, which is the wireframe, and the deformed mesh, which is the one with the color contour here. All right, I use scaling quite a bit. We'll go 10 times here. The amount you scale is really dependent on how much warpage you actually have with respect to the size of your part, which might depend on the material type that you're using or the structural rigidity of your part geometry. But scaling allows you to really visualize the warpage a little bit better. So for example, we can see that this feature here is very obviously warping inwards, right? This surface is really kind of warping inwards. Whereas something like this on the same magnitude really isn't going anywhere. Maybe a little bit downwards, but it's mostly just going inwards. It's not really going laterally at all. Let's check it out this way. Yeah, maybe like a little bit, maybe a little bit right, but in general, this is really, it looks like it's just going straight inwards, whereas this guy actually looks like it's kind of warping. And one very important note to make about the total displacement results is that there's actually two shrinkage information sets that are tied into the displacement. There's the material shrinkage, or the natural linear shrinkage of the material. And then there's what we call the differential shrinkage, which is, more commonly referred to as warpage. All right, so material shrinkage and the warpage are tied into the total displacement, which is why you see the color contour is the same between this region, which looks like it's just linearly shrinking, and this region over here, which is very obviously warping. All right, so how do we separate those two? How do we know which of these regions is warping versus which of these regions is shrinking besides just looking at it visually? Well, that's where the compensation tool comes in. All right, so the compensation tool allows us to compensate for the material shrinkage, effectively removing it from the result and only leaving behind the warpage of the material or of the part. All right, so what I'm going to do is I'm going to set an isotropic compensation. Isotropic, just a fancy word meaning that all the X, Y, and Z will be set to the same percentage. And we just input the material shrinkage value of this particular grade, which for this PCABS material, I'll tell you is 0.5% or 5,000ths of an inch per inch. And we see the color contour now changes drastically. Like I said, this removes the linear shrinkage. So any region that was a high displacement and is no longer a high displacement after the compensation was linearly shrinking. So obviously I'm going to pay attention to this guy right here. We saw that this was red without the compensation. Just go back to 0 real quick just to show you. So this was red with 0 compensation, but once I input, oh, now 50%. There we go. So once we have our compensation input, we see that this goes back to a blue color, whereas this guy down here is still red color. So all that really means is that we've returned, or we've effectively removed the material shrinkage from the equation, and we are just left behind with the warpage. So the regions that are high displacement now are actually warping. I don't even know if I have to say why this wall is warping. It should be pretty obvious. The hot pocket that we had down here, the hot spot that we had in this channel region is going to pull all these surfaces inwards. This one included, because it has such a high degree of freedom. The surface is just going to be pulled inwards. We already knew that pretty much from the cooling results. But also something that might not be as obvious, we see that this region here was linearly shrinking quite a bit. That's actually likely a result of what was happening in the filling and packing, that shear dominated flow, like I mentioned before. Remember, it kind of hits a double whammy of high shrinkage. You have a high temperature material that is not very well packed out. That's going to shrink quite a bit more than, for example, what's happening around the gate region. All right, I have a couple more results that I want to show off here before we end off this session. The first of which is called the measure distance tool. Measure distance is really, really awesome when we're looking at warpage total displacement specifically, because although the function by itself seems quite simplistic, I can just measure the distance between 2 points. If I'm in the total displacement result and I click save and close, it actually gives me a couple more data points. It gives me the model distance, it gives me the deformed model distance, and it gives me the linear shrinkage between the two. That information can be invaluable, right? This sort of information can be directly applied to a tolerance sheet to see if your part is going to hit a specific criteria or not. All right, so for example, let's say I have this point up here. Use the mesh snap. You can use your mesh snap down here at the bottom right to make it a little bit more precise. Let's say I have this corner and this corner over here. Maybe I have a tolerance that I need to hit between those two. Click save and close. And we can see just how much more the linear shrinkage is in this region than what we had as our natural material shrinkage. All right, you can also use this deformed distance to just try to see if you're within that plus or minus. All right, so I can actually, once I'm done with these, you can actually just highlight them and delete them. I'll leave behind these little probe nodes that you can also get rid of as well. So very easy to get rid of once you're done with them. Now, the last tool I want to show off is the flatness function. So flatness is actually a newer function to Moldex3D Studio. So if you've been using the older interface, you might not be as familiar with this, or actually flatness might mean something completely different to you than what we have here in Studio. So flatness allows me to select any element on my part. That element will be propagated out to the rest of my surface based on the feature line constraints. And then based on the element that I clicked on, that's going to create a flatness plane. And then we get a flatness distribution across that singular surface. So it isolates that surface from the rest of my part geometry. And we can just see how much deviation we have between the extremities of this surface and the element that I originally clicked on. So very, very useful type of result here. You can also deform this surface by going into the deformation function, which is kind of cool sometimes. All right, and that's really the last result that I wanted to show off. At this point, I am going to open it up to question and answer. I think each and every one of you, we had a huge turnout today, and I really appreciate everybody for coming out and learning a little bit more about Moldex3D. If you do have any questions, feel free to post those into the chat, or if you have any questions after the training, feel free to reach out to us at either sales.us@moldex3d.com or support.us@moldex3d.com, and we'll be happy to answer your questions for you. But like I said, I'm going to transition it over to a question and answer, and we'll be answering some questions live. So definitely ask your questions over in the chat function. And we hope to see you in the next Moldex3D online training series session.